And now for a proof of the diagonalization theorem. Okay, diagonalization theorem says if we have A as an n by n matrix with distinct eigenvalues, C1 through C sub k, with corresponding algebraic multiplicities, m sub 1 through m sub k, then matrix A is diagonalizable if and only if the rank of A minus C sub I times the identity equals n minus m sub I, that holding for all relevant indices I. In other words, the rank of A minus eigenvalue times identity is n minus algebraic multiplicity of that eigenvalue. And this isn't a surprising matrix to consider. A minus C sub I times I, well, A minus Ci, determinant of, yields the characteristic polynomial, and that's where the C sub i's come from. So you're looking at A minus Ci, where you've kind of evaluated C at C sub I, a known eigenvalue of the matrix. All right. Well, if I know we have an eigenvalue of this matrix, I know the determinant of A minus C sub I times I is 0. I know A is not invertible. I know A minus C sub I times identity matrix is not invertible. And so it has to have a rank less than n. Okay, but this gives conditions between diagonalizability and the rank of such matrices. So let's go through that. Okay, for sufficiency, that is, if A is diagonalizable, if A has rank satisfying this, then A is diagonalizable. All right, suppose we have this, the rank of A minus C sub I times the identity equals n minus m sub I for all appropriate indices. Okay, theorem 3.5.4 tells us the dimension of the null space of a matrix is n by n matrix minus the rank of that matrix. And I tell you what, let's take a peek real quick at theorem 3.5.4. Theorem 3.5.4, here we're dealing with a square matrix. The nullity of n by m matrix A satisfies the dimension of the null space equals m minus the rank. We have n and m equal in ours. So this is exactly what we're looking at. Dimension of the null space equals m minus the rank. This led us to talk about the rank nullity equation. So that's actually what we're dealing with in this statement. Okay, so we get the dimension of the null space of that matrix is n minus the rank of that matrix. N minus the rank equals m sub I, if you'll rearrange this little formula here. So we get an m sub I out there. So the null space of A minus C sub I times the identity is simply by definition all vectors, all n vectors, that are mapped to 0 when multiplied by that matrix. A minus C sub I times identity times vector x equals 0 vector. The definition of the null space, it's the vectors mapped to the 0 vector by that matrix. Okay, well, we know the dimension of the null space is m sub I. That's this computation in the previous line. So there are m sub I linearly independent x satisfying this condition, ax equals c sub I x, equivalent to saying a minus c sub I times the identity times x equals 0. Distribute the x and rearrange, and it produces this. And so we see that these linearly independent m sub i's, the number of elements of a basis for the null space, consists of eigen vectors associated with C sub I. So these m sub I vectors are linearly independent. These m sub I vectors, in fact, are a basis for the eigenspace associated with that eigenvalue. So for eigenvalue C sub I, we've found M sub I linearly independent eigenvectors. Theorem 3.8.8, as we did that relatively recently, says eigenvalues associated with distinct eigenvalues are linearly independent. So here's the number of linearly independent eigenvectors we have altogether. We've got M sub 1 linearly independent eigenvectors associated with C sub 1. We've got M sub 2 linearly independent eigenvectors associated with C sub 2. And since C1 and C sub 2 are different, we listed these as distinct eigenvalues was the setup. Then the eigenvectors associated with C sub 1 are linearly independent with the eigenvalues associated with C sub 2, and so forth. So to find the number of linearly independent eigenvectors, we just sum up the M1, M2 up through M sub k. These were algebraic multiplicities of altogether the eigenvalues of matrix A. The eigenvalues are zeros of the characteristic polynomial. We're dealing with an n by n matrix. That characteristic polynomial is degree n. Fundamental theorem of algebra says when you add up all those multiplicities, you get n out. So summing the m1 through m sub k gives us n linearly independent eigenvectors for matrix A. All right, and that's leading us to the idea that when we make matrix V, the way we make matrix V using eigenvectors of matrix A, this matrix V will have linearly independent columns, those columns being the eigenvectors. We just argued all n of them are linearly independent. So the rank of V is n, so V inverse exists. So make matrix V by using that list of linearly independent eigenvectors we just found. V will have rank n, V will be invertible, and we'll use that to show that A is diagonalizable. So we'll let C be the diagonal matrix with the eigenvalues, as we always did when we did this diagonalization stuff, associated, with corresponding eigenvectors. Then we have A times V equals V times C. Theorem 3.8.10 gives us that. We know V is invertible, so we can take this V, move it to the other side on the right to get a V inverse, and there's the diagonalizability of matrix A. So we're claiming A, let's go back and look at the statement. We're claiming A diagonalizable if and only if this rank deal holds. Okay, we've shown the rank equation, well, this equation involving rank, I should say, implies diagonalizability. All right, so now we want to assume diagonalizability and deduce that equation involving rank. Okay, so suppose A is diagonalizable. That means A equals V, C, V inverse for some invertible V and some diagonal matrix C. Not necessarily, well, not yet, the eigenvalues and eigenvector stuff, but if we have this relationship, multiply on the right by V, gives us AV equals V times C. Oh, well, Theorem 3.8.10 says the only time you can have that is when C is a diagonal matrix with eigenvalues along the diagonal, and matrix V is a matrix whose columns consist of corresponding eigenvectors of matrix A. Jth column of matrix V being an eigenvector corresponding to C sub j, the jth diagonal entry in matrix C. All right, so ultimately we are led to that relationship between diagonal matrices containing eigenvalues and these vectors, these matrices V containing corresponding eigenvectors. So as warned in the past, we actually get a lot of mileage out of this Theorem 3.8.10 in these conversations of diagonalizability. V is invertible. We're working under the hypotheses that A equals VC V inverse. V is invertible, so the rank of V must be n. And so the eigenvectors in V must be linearly independent. The rank was, say, the dimension of the column space. Okay, we've got n columns in matrix V. If the rank of V is n, those columns form a basis for the column space, and they must be linearly independent because a basis is a linearly independent spanning set. So the eigenvectors in V are linearly independent. We have repeated eigenvalues in matrix C according to multiplicity. Right? We have C1 through C sub n are listed here as the eigenvalues of A. Nobody said the eigenvalues were distinct in any of this. So these are the eigenvalues. We put them in a matrix. If C1 and C2 happen to be the same, fine. We just repeated the same eigenvalue more than once according to the algebraic multiplicity to get a kind of a complete collection of eigenvalues. Okay, so I between 1 and k, the diagonal matrix C minus C sub I times I, this is what we were talking about in the theorem, has m sub I zeros on the diagonal. Well, that's because, hey, when I look at C, this diagonal matrix with the eigenvalues as entries, subtract C sub I times I, well, this is a diagonal matrix as well. The C sub I times the identity matrix is a diagonal matrix with all C sub I's along the diagonal. C sub I will be repeated as a diagonal element of matrix C up here, m sub I times, like we said, repeated according to multiplicity. Here it is, repeated according to multiplicity. So we might get C1, C1, C1 3 times, for example, if m sub 1 equals 3. So if it's algebraic multiplicity 3, repeated 3 times, meaning when you take this difference of matrices, 3 times this one would have a value on the diagonal. This one's got that value on the diagonal all of the time. Then that'd produce 3 zeros in the matrix difference along the diagonal. All right. So that matrix difference has exactly m sub I zeros on the diagonal. All right. Then if we look at the rank of C minus C sub I, the rank of C minus C sub I times the identity, that'll be n minus m sub I. Why is that? We're dealing with multiples of, as columns, we're dealing with multiples of the standard basis vectors, except you've lost some of those vectors. M sub I of them have been replaced with 0 vectors. So we get how many linearly independent columns? All the non-zero ones will still be linearly independent, of which there are n minus m sub I. V and V inverse are invertible, being the inverses of each other, and so they're a full rank, and so we can do the following. N minus m sub I equals the rank of C minus C sub I, and we just said that. Theorem 3.3.12 said I can multiply on the left and the right by V and V inverse, a matrix and its inverse, and that doesn't change the rank. That's the claim of Theorem 3.3.12. If we'll distribute the V and the V inverse, that'll produce rank VC V inverse. Here, here the V and the V inverse and the identity will all get together, leave us with nothing but an identity there. VC V inverse, why, that's matrix A, so we can replace this with A minus C sub I times the identity. We've shown the rank of A minus C sub I times the identity is n minus m sub I, and that was the claim. All right. So, whoops. There we go. So, back to the notes, 3.8 notes. So we've got the diagonalizability theorem. What this says, I think I mentioned this in the past, is this little condition really boils down to, maybe you spoke about it this way in linear algebra, a matrix A is diagonalizable if and only if every eigenvalue has equal algebraic and geometric multiplicities. We've dealt with an algebraic multiplicity right here. Geometric multiplicity is related to, well, it's related to the null space of something or other. We'll deal with it in terms of null spaces here shortly. But this is ultimately saying n by n matrix A with distinct eigenvalues. So we've listed them distinctly here, and given algebraic multiplicities is diagonalizable if and only if the algebraic multiplicity of each of these eigenvalues, is given down here, equals their geometric multiplicities. And the geometric multiplicity is related to the dimension of something or other. All right, it's a little indirect in how it's spelled out here, but more of that when we explore null spaces. Okay, we can use this result to show that a matrix is not diagonalizable. Consider this matrix A is given. I'm going to ask you to believe me on some of these computations. The characteristic polynomial, c squared minus 8c squared plus 13c minus 6. Do your thing, taking determinants. This factors into c minus 6 times c minus 1 squared. So if we look at eigenvalue, c equals 1. It's of algebraic multiplicity 2. So here's where we'd make matrix C. The diagonal matrix we were talking about would be of the form, say 1 along the first the diagonal elements would be 1, 1 again, and 6. So you'd repeat the 1 twice according to its algebraic multiplicity when making the diagonal matrix, if this works. But it doesn't work because we're going to check this rank requirement. We'll take the rank of A minus 1. We're looking at an eigenvalue of 1 times the identity matrix. Here it is. Rank of A minus 1 times I. That's this particular matrix. We just subtracted the identity. It reduces each of the diagonal elements in A by 1 to produce this. Do your thing of computing rank, row reduce and count pivots, for example. Trust me, that's going to give you out of 2. But that doesn't equal n minus m sub I. N is 3. You're dealing with a 3 by 3 matrix. The multiplicity associated with this eigenvalue is 2, and that little 2 right there. So we get 3 minus 2 equals 1. That's what the n minus m sub I thing is, yet the rank of this matrix is 2. Those ain't equal. It was if and only if result. This matrix is not diagonalizable. Okay, so there's a quick little numerical application. I hadn't done too many of those in this level class. Gentle, page 117, the author of the text argues that a symmetric matrix is diagonalizable. We go a little bit further than that. Something more general holds. And I've gone to a different source. Here's the source for your information, a website out there on orthogonally diagonalizable matrices from a University of Washington in St. Louis professor, still available in 2020. And the claim is that a real n by n matrix A is orthogonally diagonalizable if and only if that matrix is symmetric. Okay, so we've claimed not simply diagonalizable, but orthogonally diagonalizable. Diagonalizable using like a V and a V inverse that are orthogonal matrices. So in that sense, it's a more general claim than what's mentioned in our textbook. And let's look at a proof of that. Okay. Real n by n matrix A is orthogonally diagonalizable if and only if it's symmetric. Okay, first suppose it's orthogonally diagonalizable. This part's easy. The other part's a little lengthier. Let A be orthogonally diagonalizable. Say C is a diagonal matrix and Q is an orthogonal matrix such that A equals Q, C, Q transpose. That's what orthogonally diagonalizable means. Orthogonal matrix and its inverse or its transpose. Same thing for an orthogonal matrix. Q transpose equals Q inverse for orthogonal matrices, we argued earlier and have used repeatedly. So we get Q, C, Q transpose. C is diagonal because that's what orthogonally diagonalizable means. If we transpose this, take A transpose. Remember, we're trying to show A is symmetric in this one. Take the transpose of A. That's the same as the transpose of this. Produces Q transpose, transpose, C transpose in the middle, Q transpose on the right. Q transpose transpose is Q. C transpose is C. Remember, C is a diagonal matrix, so it's symmetric. So it equals its transpose. We get a C out here as well. And Q, C, Q transpose, why that is matrix A. So A transpose equals A, and that's our very definition of symmetric. Piece of cake, orthogonally diagonalizable implies symmetric. How about the converse? Okay, this will take a little while. Suppose A is symmetric. So in the following, A is symmetric, A equals A transpose. We're trying to show A is orthogonally diagonalizable, and we're going to do it inductively. All right, suppose the dimension's 1, just to get a base case in. We can take Q to be the matrix consisting of 1, and we have A equals Q, A, Q transpose. A itself, if it's a 1-by-1 matrix, is by definition, it's a diagonal matrix. This is an orthogonal matrix, it equals its inverse. I'm sorry, its transpose equals its inverse. A little uninteresting with 1-by-1 matrices, but it establishes a base case and shows that A is orthogonally diagonalizable. Here's Q and here's C. Take C to be A itself. Now suppose the result holds for n-1 by n-1 matrices. So suppose all n-1 by n-1 matrices have the property that when they're symmetric, then they're orthogonally diagonalizable. We're going to show n by n matrices have that property as well, and induction shows it holds for all n. Okay, we're taking A to be real and symmetric. Theorem 3.8.7 tells us under those conditions, all the eigenvalues of A are real. I think I mentioned in the past, when making up questions of find eigenvalues, hey, symmetric matrices are good things to use for questions on that because you're guaranteed that you'll have real eigenvalues, symmetric real matrices. So we know the eigenvalues of A will be real. Let C be some eigenvalue of A. If V is an eigenvector of A associated with C, then we have the determinant of A minus C times I equals 0. All right, that's how you find eigenvalues. So we're treating C as a specific eigenvalue, what's in this case. A and C are real. So we know things about systems of equations involving real numbers. I wouldn't be surprised if most of that stuff doesn't hold for complex numbers as well. But we're restricting ourselves up here to real numbers. Since A and C are real, then the system of equations with this coefficient matrix, think of X as the unknowns equals 0. This has a non-trivial real solution, namely eigenvector V. So we know by having chosen an eigenvalue and an eigenvector, this system of equations, this homogeneous system of equations, has a non-trivial solution, X equals V. All right. Let's take that V vector that we just were discussing. It's an eigenvector with associated eigenvalue C. And let's normalize it. Call that V sub 1. We're about to Gram-Schmidt some stuff. So let's go ahead and change the magnitude of that vector. Of course, if we have an eigenvector for an eigenvalue, any non-zero scalar multiple of that eigenvector is also another eigenvector for the given eigenvalue. So scaling eigenvectors doesn't change the fact that you're still dealing with eigenvectors. Scalar multiples of eigenvectors are eigenvectors when you don't use the scalar 0, because we didn't count 0 vectors as eigenvectors. So anyhow, this V1, it's a unit vector. It's also an eigenvector. What we're going to do is take a set consisting of just this one unit vector and expand it to an orthonormal basis of Rn, say V1 through V sub n. We did this, I guess, in the proof of Theorem 3.8.9. The way we did it was say, okay, take this set right here consisting of this single little vector and throw in the n standard basis vectors for Rn. Now you got yourself a collection of n plus 1 vectors. Okay, they can't be linearly independent if they're vectors from Rn. There's one too many. Perform the Gram-Schmidt process to that collection of vectors. Gram-Schmidt process will keep this first vector. It's already a unit vector, by the way, so it keeps it as is. That's why we normalize it up here. So it keeps that first vector, and as you go through the Gram-Schmidt process with the remaining n vectors, you're going to lose one of them. When you do that, project and subtract and normalize stuff, one of them will disappear. You'll be in the end left with an orthonormal basis of Rn, and it will include V sub 1 as the first vector, as we've denoted things. And the other vectors, I know almost nothing about vectors V2 through V sub n. Oh, they came out of the Gram-Schmidt process. Okay, they'll be orthonormal. I know that much. So V2 through V sub n, these are all unit vectors. They're all orthogonal to each other, and they're all orthogonal to V sub 1. All right. Form an n by n matrix P using these vectors up here as the columns of matrix P. Let the ith column be vector V sub I for I ranging from 1 to n. All right. Hey, that means P is orthogonal. Right, its columns form an orthonormal set. That's the very definition of orthogonal, remember? So P is orthogonal. Well, then that means P inverse and P transpose are the same thing. A theorem from Theorem 3.7.1, a property of orthogonal matrices. All right, consider P inverse AP. Remember, we're going for showing symmetry in this. P inverse AP is P transpose AP by substituting. We're going for orthogonally diagonalizable. We're assuming symmetry, excuse me. This matrix is symmetric because if we'll transpose it, we get, let's see, P transpose on the left, A transpose in the middle. So I know we're going to replace that with A, so excuse me, yeah, we were assuming symmetry. P transpose transpose on the right. Okay, that gives us a P on the right, a P transpose up front, and I'm sorry, we're in this assumption that A is symmetric. All right, so A transpose equals A. So this matrix, P transpose AP, when transposed, equals itself. So this matrix is symmetric. So P transpose AP is symmetric. We're going to pick the first column off of P transpose AP. All right. The argument here is not complicated. I can't imagine I would ever thought of all this manipulations of P transposes, and we've only begun to manipulate some of these matrices. But this is really just a computational argument, which means they're probably fairly easy to follow the computations. Coming up with the computations, that's a whole nother story then. We're going to look at the first column of the matrix P transpose AP. So we got a matrix here. We're going to multiply it by the column matrix 1, 0, 0, 0, 0, 0. And think what happens. We'd have first row, first column. Second row, first column. Third row, first column. Whenever we do that, you pull one of these rows out of this matrix, the first entry's pulled off and all the others are lost because of these zeros. We do inner products with rows and columns when we take matrix products. So in fact, what you would keep is the first component of the first row, the first component of the second row, the first component of the third row, and so forth. You'd keep the first column. That's what it amounts to. So multiplying by this matrix pulls off the first column of P transpose AP. We're going to show, next slide, that this is something particular. First, hey, that applies when I take P and multiply it by this matrix as well. P times this matrix of 1 followed by a bunch of zeros will pull off the first column of matrix P. First column of matrix P was what? V sub 1. We made matrix P by using V1 through V sub n as the columns of that matrix. Okay, so P times this thing here will give us the first column of P, which is V sub 1. We constructed it that way. Remember, I don't know too much about V2 through V sub n, but I know a bit of stuff about V sub 1. It's an eigenvalue. The other things, maybe not. I don't know. The other things are orthonormal. I know that, but I don't know anything about eigenvalue properties of V2 through V sub n, but I do about V sub 1. Why? V sub 1 is an eigenvector associated with eigenvalue C. So I can replace A times V sub 1 with C times V sub 1, definition of eigenvector and eigenvalue. C is a scalar. We can scoot it over to the left. That gives us P transpose times V sub 1. P itself, again, was made out of these vectors as column vectors. So let me rewrite the P as V1, V2 through V sub n. Notation I need to keep an eye on. This is a standard type thing we've done where these are the column vectors of matrix P and transpose it. So I've just written P out in terms of columns, these vectors we have above. We got a transpose here. We got a scalar C out front, which by the way was an eigenvalue. And let's see what happens on the next page. So next page, we'll go through and transpose this matrix. All right, that means take that matrix, which was strictly speaking given as a partitioned matrix laid out in rows, transpose it, we get a partitioned matrix laid out in columns, and we transpose each of the pieces of the partition. That's how the transposing is accomplished. We've got a vector V1 over here. Let's put it inside. So do the multiplication. We're really multiplying partition matrices here. And we get V1 transpose, V1, V2 transpose, V1, blah, 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 blah. When you get a transpose on the first one and not the second one, and we're dealing with column vectors, which by standard convention we are, these are just inner products. So we've got the inner product of V1 with V1, the inner product of V2 with V1, the inner product of V sub n with V1. I didn't know much about V2 through V sub n, but I knew they were all perpendicular to V1. They're all perpendicular to each other as well, but in particular, perpendicular to V1. Inner product of V1 with itself, that'd be the norm squared of V1. We had normalized V1 so that it has a norm of 1, so we get a 1 there. Orthogonality and all these others produces a bunch of zeros. Take that C inside, get this. What was this again? This is the first column of the matrix, P inverse AP or P transpose AP. Here's the first column. We argued above that this thing is symmetric. So the first row is just the transpose of this. All right, we just found out that P inverse AP is of the following form. We can put C, that eigenvector that we started with here. We get zeros for the remainder of the first row, right, and zeros for the remainder of the first column, right. So we're presenting it as a partitioned matrix. So let's see, this is actually, this 0 here represents this 1 by, well, we have the C over there, it represents a matrix or a vector of all zeros, or a matrix, a 1 by n minus 1. So this represents n minus 1 row vector of all zeros. This represents an n minus 1 by 1 column vector of all zeros. So these zeros aren't just scalars, right? They're appropriately sized zero matrices. And then we get some stuff left over down here. But remember, we showed P inverse AP is symmetric. P inverse AP is symmetric. We did it upstairs with transposes. So it must be that this matrix is symmetric as well. So this piece of the partition, call it matrix B. It's n minus 1 by n minus 1. We've removed a row and a column from an n by n matrix to get this, if you like. And it must be symmetric as well because the big matrix is symmetric and it lies, you know, along the diagonal in a sense. Well, by the induction hypothesis, we assume that all n minus 1 by n minus 1 symmetric matrices were orthogonally diagonalizable. So matrix B can be written as U, D, U inverse, where U is an orthogonal matrix and D is a diagonal matrix. Since U is an orthogonal matrix, we could also write that as a transpose, if you like. You can solve this equation for D. To get D equals, move the U and U inverses to the other side, and you get D equals U inverse BU. Keep that in mind that we're going to use here in a little while. All right, so what we did was apply the induction hypothesis, that being if we have an n minus 1 by n minus 1 symmetric matrix, then it's orthogonally diagonalizable. There exists a diagonal matrix D and an orthogonal matrix U such that that symmetric matrix can be written as this product. Rearrange it to get D equals U inverse BU because we're going to use that in the future on the next slide. All right, so how are we doing here? We're trying to show A is orthogonally diagonalizable. We've shown this is orthogonally diagonalizable. All right, we use the induction hypothesis. The problem will be is it's too small. So we need to get from an n minus 1 by n minus 1 matrix to an n by n matrix. Here's an n by n matrix right here, by the way. Okay. We're going to define, I warned you about this, some more matrices. Should be easy enough to follow, but what inspires this? Not so inspired, actually. For this matrix U, this n minus 1 by n minus 1 matrix U that we were just discussing in relationship to matrix B, define matrix R to be this partition matrix. So we've taken that matrix U and we've tacked on a 1, 0 as appropriate. 1 in a column of zeros, a 1 in a row of zeros. This R, what it's got going for it is it's somehow intimately related to matrix U, and it's n by n. Notice we can find R inverse easily enough. We just invert that lower right-hand part, easily checked by the definition of multiplication of partition matrices. Hey, U inverse and U transpose are the same. U was an orthogonal matrix involved in the orthogonal diagonalizability of matrix B. So we make a substitution there, and lo and behold, you've got the transpose of R. So R inverse equals R transpose. That right there tells you, hey, R is an orthogonal matrix as well, because its inverse is its transpose. Let's define another matrix. Q equals P times R. All right, this Q is the invertible matrix that we're looking for. So we're done defining matrices, and we're 3 or 4 levels in on this. So we got to climb out of that hole and get back to a conversation about A and some orthogonal matrices. But let Q be P times R. P, we had above, has its columns, those V sub 1, V sub 2 vectors, those vectors that formed an orthonormal basis for Rn. And R we just defined. So define Q to be P times R. Let's take Q times Q transpose. Well, Q is P times R, okay. So Q transpose is P times R transpose. Transposing a product, do the transpose, reverse the order in the product. Hey, we got an R times R transpose. R transpose equals R inverse. That's gone. You got P transpose times P. Hey, P was an orthogonal matrix, So its transpose is its inverse as well. And all this stuff simplifies down to an identity. Oh, then Q is invertible and its inverse is Q transpose. In other words, Q is orthogonal. Theorem 3.7.1, I think it was. When we used it so many times, I remember the number. But showing Q transpose equals the identity shows that Q is an orthogonal matrix. All right, so that's a big deal. Q is an orthogonal matrix. We're trying to show orthogonal diagonalizability of matrix A. Q's got two things going for it. It's orthogonal and it's n by n, right? It's the same dimension as R up here. It's n by n, so it's the right size and it's orthogonal. Let's multiply A on the left by Q inverse, on the right by Q, and we've done this. We've pulled off the computation, provided we can show this is a diagonal matrix. Okay, well, Q is PR, so Q inverse is R inverse P inverse, so substitute that in. Rewrite the A, Q is PR, make that substitution. Let's associate the inner stuff, P inverse AP. We saw, previous slide I think it was, that P inverse AP can be written like this. So we'll make a substitution there. We got the R inverse on the left and the R on the right. Having made that substitution, let's look back and make sure P inverse AP actually equals this partition matrix. Going back. Here it is right here. P inverse AP is this matrix. What was up with this? B is symmetric. So this matrix down here is symmetric. Back to where we were. Okay, so we've substituted for this symmetric matrix here. Okay. You know what R inverse is, don't you? Yeah, R inverse is this. So we'll substitute that for R inverse. R itself has this as its definition. We'll put that in there. So we substituted for R inverse and R. Do your partition matrix multiplication, and that'll lead you down to this 2 by 2 partitioned matrix. Maybe I shouldn't call it that. It's a partition matrix with 4 parts. Okay. U inverse BU, does that ring a bell? Wasn't that diagonal matrix D from the previous slide? Let's run back and look at that too. So U inverse BU is diagonal matrix D. U inverse BU is diagonal matrix D. Diagonal matrix D came out of the induction hypothesis. All right, so D is diagonal. When we left off here, we've got one entry here, a scalar here, a row of zeros, a column of zeros in these positions, and a diagonal matrix there. Oh, if that's a diagonal matrix, this whole thing is a diagonal matrix. D was an n minus 1 by n minus 1 diagonal matrix. This thing here, an n by n diagonal matrix. And arguably we're done. Let's elaborate a little bit. So we've taken Q inverse AQ and produced a diagonal matrix. We did it computationally in a sense. We confirmed this by bunches of matrix multiplications. Now there's some mystery buried in this, like where did matrix D come from? Well, it came out of the induction hypothesis. So I wouldn't say this is a computational technique, but I would stand by my claim that it's a computational proof. Take the Q's to the other side. So let's get the Q inverse and the Q on the other side of this equal sign. So they'll pop up with a Q on the left and a Q inverse on the right. The Q inverse can be written as a Q transpose because Q is an orthogonal matrix. It says it right there. So we've got A equals Q, let's call this matrix C, Q transpose. A equals Q, C, Q transpose, where this is matrix C, and this is a diagonal matrix. And that's what diagonalizable means. Q is orthogonal, C is diagonal, matrix A is orthogonally diagonalizable. So the result holds for n by n matrices. So by induction, the result holds for all square matrices. That is, if we have symmetry, then we have orthogonal diagonalizability, orthogonally diagonalizable matrices. All right, so that one was a little lengthy, but I stand by my claim. It's mostly computational. So real n by n matrix is orthogonally diagonalizable if and only if it's symmetric. Now, if we don't have symmetric matrices, that doesn't mean they're not diagonal. That means they're not orthogonally diagonalizable. Just as an observation, this is a little extra constraint that's been put in about using orthogonal matrices to do the diagonalization stuff. Next result, Theorem 12, says if A is an n by n diagonalizable matrix, say it can be written in this form here, A equals V, C, V inverse, where C is diagonal, then there are n linearly independent eigenvectors of matrix A, first off, and secondly, the number of non-zero eigenvalues of A is equal to the rank of A. How you feel about this? You okay with having eigenvalues that are zeros? Yeah. Just not okay with having eigenvectors that are zero. Eigenvalues could be zero. The eigenvectors associated with an eigenvalue of zero, see if you can process this. There's a lot of moving parts. The eigenvectors corresponding to an eigenvalue of zero, that's the null space of matrix A. You take the determinant of A minus 0i, the determinant of A. You consider that A is a mapping. A times a vector equals 0. That's the null space. So yeah, I'm happy with having zero eigenvalues. We can't allow 0 as an eigenvector is the rules. All right, so the claim is the number of non-zero eigenvalues of A is equal to the rank of A. So let's establish those two things. Okay, A is diagonalizable, can be represented like this. First claim, there are n linearly independent eigenvectors of A. Okay, well, we're hypothesizing in both of these that A equals V, C, V inverse. We can cross multiply, as it were, multiply both sides on the right by V, I should say. And we get AV equals V times C. Well, you know, by theorem 3.8.10, promised you mileage out of that one. This only occurs when the columns of V are eigenvectors of A corresponding to diagonal entries of C. The usual thing. The ith column of V is V sub I, where V sub I is an eigenvector of value C sub I, and C sub I appears in the ith slot, the II entry of diagonal matrix C. All right, we know V is invertible because we've assumed this stuff up here happens. So the rank of V must be n, it must be a full rank matrix to be invertible. Rank is also the dimension of the column space. So the columns of matrix V are linearly independent. The dimension of the column space is n. The span of the columns is n. There's n columns. So it follows that those columns form a basis for the column space of V, and the columns must be linearly independent. A basis is a linearly independent spanning set. So we draw a conclusion that the columns of V, that is, those eigenvalues, are linearly independent. We've got n of them. We have n linearly independent eigenvectors of matrix A. The eigenspace is n-dimensional, is what we're getting. All right, second part, the number of non-zero eigenvalues is equal to the rank of A. So it's a question about the rank of A, and somehow we got to get to the non-zero eigenvalues, or equivalently, we got to find the zero eigenvalues of matrix A and relate it to the rank of A. All right. So in this case, we're still with this assumption. So we're assuming V is invertible. We're, in this case, assuming diagonalizable. So we're not assuming initially that, I don't know, V contains vectors and C contains eigenvalues. We can easily draw that conclusion like we did in part 1, but the setup is A equals VC V inverse, where C is diagonalizable. All right, V is invertible, so it's got to be a full rank. That's what invertible is. By theorem 3.3.9, there are matrices P and Q, products of elementary matrices, such that P times V times Q equals the identity. What's that mean? Let's see. V is full rank. V is invertible. What if you tried to row reduce matrix V? You could reduce it down to the identity. Well, remember, we're using row and column operations in here, so that's why there's 2 matrices. But how would you represent those elementary row operations? By using elementary matrices multiplying on the left. How about elementary column operations? By elementary matrices multiplying on the right of V. So collect together those elementary matrices into the ones for row operations into matrix P, the one for columns operations into matrix Q. And what you're saying is, hey, if V is invertible, it's equivalent to the identity. It's simply row equivalent to the identity. You know that from linear algebra, from the way you find inverses. You augment V with an identity and you row reduce V down to the identity. And it works if V is invertible. But here's our claim, so that's what that theorem said. So it shouldn't be a surprise that that claim is true, given your experience with matrices. Every elementary matrix is invertible. And the notation of section 3.2, this is stuff I made up, this notation. EPQ, that's an elementary matrix that interchanges rows P and Q, has as its inverse itself. If I interchange rows P and Q, how do you undo that? Interchange them again. Swap them back. If we were to take row P and multiply it by scalar S, how would you undo that? By multiplying row P by scalar 1 over S. S can't be 0 for elementary row operations. If we were to add S times row Q to SP, that's what I indicated with this, how would you undo that? By adding negative S times row Q to row P. So there's explicitly the inverses of those elementary matrices. Anyhow, stand by my claim. Every elementary matrix is invertible. In fact, its inverse is easy to find. So the product of a bunch of elementary matrices is invertible. Product of invertible matrices is invertible. You know how to find the inverse. So these P and Q matrices we just introduced as products of elementary matrices, they are themselves invertible. So Q inverse exists. We left off on the last slide with P, V, Q equals I. P times V times Q equals the identity. Multiply both sides on the right by Q inverse. That'll produce a Q inverse on the right. Drop the identity we would pick up on the left. And we get PV equals Q inverse. Same kind of thing holds for P. It's invertible. Multiply on the left by P inverse. And we get V equals P inverse Q. So V is a product of elementary matrices because the P is a product of elementary matrices, so I can find its inverse as a product of elementary matrices, and same for Q. So anyhow, V is a product of elementary matrices. Then V inverse is also a product of elementary matrices, so we're getting lots of elementary matrices. Theorem 3.3.3 said, well, we're applying it right here. Theorem 3.3.3 said, if I take a matrix C and multiply it on the right and the left by a matrix that's a product of elementary matrices, that doesn't change the rank. Equivalently, if I multiply by an invertible matrix, that doesn't change the rank. I think it was stated in terms of products of elementary matrices, which is why we approached it like this. But the rank of VC, V inverse, is the same as the rank of C. There's why. We don't want to talk about the rank of that stuff. We want to talk about the rank of A. We're dealing with a question about the rank of A. Well, the rank of A equals the rank of VC, V inverse because A equals VC, V inverse. So substitute in there, apply that theorem to say that equals the rank of C. All right. We had C as a diagonal matrix with eigenvalues listed along the diagonal repeated according to multiplicity. So what's the rank of C? Well, every time you hit one of these diagonal entries that is 0, you got a whole column of zeros. So that's where the 0 eigenvalues come in. So if we look at the ith column of this matrix C, it's C sub I, the ith eigenvalue, times E sub I being the ith standard basis vector of Rn, the vector of a bunch of zeros, a 1 in the ith position, and then a bunch more zeros. Treat them as column vectors in this case to talk about columns of C. So we get C sub I times these standard basis vectors. Well, when C sub I is 0, you lose those. So the rank of C would correspond to the number of entries here minus the ones that are 0. So I've got scalar multiples of the ith standard basis vectors. Fine. If they're all non-zero, you're getting Rn out that they will span. If one of them is 0, you're getting Rn minus 1. That 1, 0 for an eigenvalue will produce a whole column of zeros in matrix C. I mean, the columns of matrix C are all zeros, but in one place, possibly. The entry in the diagonal makes all the decisions. If it's non-zero, we've got a column vector that's non-zero. If it is 0, we got a 0 column vector, and you're losing rank there. So the rank of C is the number of non-zero columns, that is the number of non-zero eigenvalues. And we showed the rank of C equals the rank of A. So the rank of A is also the number of non-zero eigenvalues. You lose from the rank 1 every time you run across a 0 eigenvalue is another way to think about it. So that establishes that one. And let's step aside from this proof stuff for a little while and go through some more conversational stuff. General states that for a diagonalizable matrix A, say A equals V, C, V inverse, C being a diagonal matrix, and for a function f of a scalar, we can define the following. All right, I got a bit of an argument with this. If we'll stick with polynomials, I'm good. He says we can define that function of a scalar is evaluated in a matrix by applying effectively the function to these matrix products, yielding a lot of cancellation when I raise this A to a power, which when you just say any old function, I mean, there's functions more complicated than raising to powers. Polynomials simply involve raising to powers. I'm okay with that. Exponential functions can be written in terms of series, which ultimately just involve raising things to powers, raising the argument x to powers. Take a power series for the exponential function. Hey, it's 1 plus x squared over 2 plus x cubed over 3 factorial and so forth. Well, I could plug a matrix into that and raise a matrix to any power you like. In fact, it's easy if I have a diagonalized matrix. I argue a little bit with this. I'm not comfortable with him saying any function. We certainly need some more details. This definition or this statement is fine if we got a polynomial. If you want to put a matrix in a polynomial, no problem. That means raising the matrix to powers. Okay, that's hard unless you can diagonalize the matrix. That's why you diagonalize matrices, in fact. But if we got more involved functions, and we're missing some details. If I start talking power series, and I start legitimately worrying about divergence. So we'll postpone this conversation for now about functions. I'm happy to deal with polynomials with matrices in them. We've talked about how it would be done in the past. Yeah, I don't think we talked in the past about how to compute those powers of A. Well, you would diagonalize, and then the computations of powers of A is easy. it ends up involving powers of the diagonal elements, which are eigenvalues. So we do want to put matrices into functions at some point, polynomials maybe, for sure. And I don't have to worry about any divergence if I restrict my attention to polynomial functions. Every real symmetric matrix is orthogonally diagonalizable. That was our argument a couple of theorems ago. Or was it the previous? Recently, I should say. Say A equals QC, Q transpose, or QC, Q inverse, where Q is orthogonal. Then we get AQ equals QC. All right, that means, hey, we described it with a matrix V in the past, but theorem 3.8.10 says when you have this kind of identity, then the columns of Q have to be eigenvectors of A. Matrix C has to consist of eigenvalues. Anyhow, I want to talk about these eigenvectors for a second. So if we have a real symmetric matrix, then we know this orthogonal matrix, we know when orthogonal matrix exists so that we can get to this point. And being an orthogonal matrix and containing the eigenvectors of A, that means we have a collection of orthonormal eigenvectors for that matrix A. They're the columns of matrix Q. Oops, matrix Q. Remember, matrix Q contains eigenvectors. When we have a product of this sort, eigenvectors of matrix A. Hey, if Q happens also to be an orthogonal matrix, then those columns are orthonormal. Okay, so then you got a collection of n orthonormal eigenvectors for this kind of matrix. That is, for a real symmetric matrix. Okay, we're going to look at some outer products now and a little bit more stuff related to the spectrum. I think we've mentioned spectrum in the past in the setting of eigenvalues, but a little bit more of that type of idea. Suppose V1 through V sub n are orthonormal n vectors. Then if we'll take the outer product, V sub I transpose, these are n vectors. Remember, this is a, let's see, an n by 1 column vector. So this is a 1 by n row vector. By default, when we say vector at this stage, we mean column vector. So anyhow, when I take the matrix product of these two, it's also called an outer product of two vectors, it produces an n by n matrix. The claim here is if you'll sum up from 1 to n these outer products of V sub I with itself, you'll get an identity matrix. Let's leave that as an exercise. Then what we extract from this, and that should be a straightforward computation actually, but these are not inner products. I should draw some attention to that. When I say V sub I times V sub I transpose, those are outer products. Inner products, the transpose was on the left, not the right. So these are not 1 by 1. These are actually n by n. Yeah, you add them up and you get an identity matrix. They must be n by n identity, n by n matrices. So if A is symmetric, we know from the previous comment that it has an orthonormal collection of eigenvectors, say V1 through V sub n. So, hey, having an orthonormal collection of vectors, we can do this kind of thing. So we can take A, maybe write it as A times the identity, the n by n identity. That n by n identity can be represented as the sum of outer products of those vectors. We take the A and distribute it in, distribution of matrix multiplication. Let's see, V sub I is a eigenvector of matrix A. So A times V sub I is the same as C sub I times V sub I. That's what eigenvector means. So we can replace the A V sub I with a C V sub I. And we can take matrix A and write it in terms of this sum involving eigenvalues, C sub I, and outer products of eigenvectors, corresponding eigenvectors, V sub i's. and that's got a name. We did require symmetry of the matrix to make sure we had the orthonormal vectors to make sure the identity could be represented as this summation. So this is a property strictly for symmetric matrices. If A is a symmetric matrix with orthonormal eigenvectors, V sub I, 1 to n, corresponding eigenvalues, C sub I, 1 to n, then this representation of A as this particular type of sum is called a spectral decomposition of A. All right. We've written it as a sum. We did factorizations before, but those were writing matrices as particular kinds of products. Here we're dealing with a sum. It's called a spectral decomposition. We're going to define P sub I to be the outer product of eigenvector V sub I with itself, and those are called spectral projectors. Excellent. All right, let's look at this. I'm assuming is pretty new stuff to you, pretty new stuff to me. I've seen it in this class, but we don't do this we don't cover this in linear algebra. The following example is from my favorite linear algebra book, but it's further deeper into the book than we ever get in a class. Let's take this symmetric matrix, this 2 by 2 real symmetric matrix, and let's find its spectral decomposition and its spectral projectors. Okay, trust me, for this matrix, you'll find that it's got 2 eigenvalues, 4 and -1. Associated with 4 is an eigenvector, 2 over the square root of 5, -1 over the square root of 5. Normalized it here. That's why we get the square root of 5 stuff there, so it's a unit vector. A vector, eigenvector associated with C sub 2 is this one, also normalized. That's why the square root of 5 stuff. These two vectors, what? Are they orthogonal? Sure they are. They're associated with different eigenvalues, so they'd have to be orthogonal, which is pretty clear. Take a dot product of these two. You'll get 2 square root of 5 times 1 square root of 5 plus -1 square root of 5 times 2 square root of 5. So yeah, you get 0 out. 2/5 minus 2/5 is what you get. So yeah, indeed, those are orthogonal. So let's take a sum from 1 to n of V sub I transpose. Okay, here n is only 2 because we got a 2 by 2 matrix for the sake of illustration. So we'll take this vector, this first vector, times its transpose, second vector times its transpose, do the row times column thing. This is 2 by 1, this is 1 by 2, produces 2 by 2 matrices. Yeah, we talked about that a while ago. And you do the multiplication, and that produces these two matrices. Okay, so these two matrices would be the spectral projectors in this setting, and when you add them together, sure enough, you get the identity out. So here's the spectral projectors. We claimed, make it smaller so I can see that definition up there too. We claimed with the P sub i's defined as these outer products, right? We did the outer products. We got these two matrices. Yeah, these are the spectral projectors. We claimed we could write A as a sum of eigenvalue times P sub i's times corresponding spectral projectors. So we should be able to take matrix A and write it as C sub I times P sub I. C1 times P1. C1 was 4. First spectral projector was this thing. C2 was -1 up here, -1. Here's the second spectral projector. And do the arithmetic, and sure enough, you get out matrix A. Here's matrix A up here. So for the sake of illustration, probably a new idea to you. There's some spectral projectors and spectral decompositions. What do we call it? Yeah, spectral decompositions of a matrix. Okay. The spectral projectors, they satisfy this equation. That's their very definition. We can write an identity matrix as a sum of those spectral projectors, as we just saw. So we get this kind of relationship here. Sum of spectral projectors equals I. all this coming out of initially a symmetric matrix, right? That was a setting to get this kind of behavior. And this writing the identity matrix is a sum of these things. So if we take P sub I transpose, that'd be V sub I times V sub I transpose transposed. Just do your little transpose thing. It gives you the same thing back out. We get P sub I transpose equals P sub I itself. So these P sub I matrices, these are symmetric. P sub I equals P sub I transpose, the very definition of symmetric. They're n by n matrices, they're square matrices. Multiply one by itself, P sub I times P sub I. Their very definition is V sub I transpose. So multiply those together as matrices. You can associate the inner ones. V sub I transpose times V sub I. Now that's an inner product. That's a dot product. So this outer product stuff had the transpose on the right. That's our new thing. It's been a while, not that long, since we've seen inner products written in this form. So indeed, that's an inner product of V sub I with itself. And we got into this. How was it again? The eigenvectors are orthonormal. Okay, so that's a unit vector, but we get the norm squared of that V sub I, but you know that's 1 because we've taken unit vectors in this. We can drop that. We get V sub I transpose, and that's P sub I. So P sub I times P sub I equals P sub I. We've been calling that idempotent somewhere along the line. So we get that relationship, multiplying the P sub i's together. If we multiply P sub I by P sub j, similar idea, V sub I transpose, V sub j transpose. Associate the two in the middle, that produces an inner product. Oh, if I and j are different, these are orthogonal eigenvectors. And we pick up a 0 in there, and we get a 0 over here. That's a 0, what? N by n matrix of zeros is the meaning of this. Left-hand side, yeah, that's an n by n matrix. So it's an n by n matrix of zeros, just to keep an eye on context. Okay, so when multiplying these spectral projectors, P sub I times P sub j, we get P sub I out when I and j are the same. We get 0 out when they're different, as commented. 0 represents an n by n matrix. The spectral decomposition, in terms of the spectral projectors, as given here, so we stated that above. Did we state that above? Indirectly, initially, right? So going back to the definition, yeah, this was the P sub I, this is the P sub i's. So we can express A like that, which I guess is the first time we've explicitly stated it. Yeah, A can be written in terms of this type of summation here. This was the spectral decomposition of A, just with the P sub i's instead of those outer products. A little observation about A to the k power. The eigenvalues of A to the k, or C sub I to the kth power of the eigenvalues of A, some theorem we had not too long ago. They keep the same eigenvectors, but the eigenvalues get raised to the power k. So the spectral decomposition of A to the k could be written by simply putting exponents on those eigenvalues. The eigenvectors will stay the same, so we get the same spectral projectors. Okay, for A asymmetric matrix, we know we can write A as this spectral decomposition. If we take the columns of a vector V to be these V sub i's, okay, symmetric matrix is going to have a collection of orthonormal eigenvectors. So matrix V will have a collection of orthonormal eigenvectors. If you like, you can choose them in different ways, but we've observed we could choose them to be orthonormal. Anyhow, that'll give us that the rank of V is in its full rank, it's invertible. We have the V is invertible when we start with a symmetric matrix. So if we take any vector, X and Rn, and we define, we require X to be V times B. Okay, what's up with this? That's a linear combination of the columns of V. You take B to be a vector in Rn. All right. Let's see, I've got the logic a little off there. We start with X, say is given. The claim is X can be written in the form V times B for some vector B. The plan being, if V is invertible, its rank is n, its columns are linearly independent, then its columns form a basis for Rn. And anything in Rn, like vector X, can be written as a linear combination of the columns of vector V. And that's exactly what this is. It's a linear combination of the columns of vector V with the coefficients given by the components of vector B for some components, for some vector B in Rn. In fact, it's a unique choice for the vector B. B must equal V inverse times X. Given X, that determines B. Remember, V was invertible. V is invertible. We looked at quadratic forms some number of sections back. That was a product of the form X transpose AX. We did only do that for square matrices. We saw ultimately that without loss of generality, we can assume these are symmetric matrices. Any quadratic form for any square matrix can be represented using a symmetric matrix. The same quadratic form, but using a symmetric matrix. It's a homework exercise I commonly assign on the section 3.2 stuff. We might need the symmetry stuff to have the conversation about the orthonormal eigenvectors. So if we take X equal to VB, as given up here, then we can take that quadratic form, X transpose AX. Matrix A can be written in terms of its spectral decomposition. Vector X can be written as VB on both sides. So we get this kind of substitution here. VB transpose is B transpose, V transpose. Transpose them both, reverse the order, stick them inside that summation. Let's stick the VB on the right-hand side inside that summation as well. All right, so this quadratic form has come down to something of this type. Okay, let's see, what have we done with this equal sign? We've got a scalar in amongst all these other vectors or matrices. Let's call them matrices. I mean, vectors are matrices, right? Well, let's take that scalar and move it over to the right. That's what we've done in that little equal sign. Okay, so we can move the scalars around as needed, as you know. Now, V sub I transpose V would be a 1 by n vector. I think what you do here, V sub I transpose, that'd be a row vector. V sub I transpose is a row vector. So when we did the matrix product, we do row times column. So first entry of first row, first column of V. First row, second column of V. First row, third column, and so forth. Well, those columns of V, let's denote as V1 through V sub n, as we've often done. I mean, these are the eigenvectors of matrix A. So that's where matrix V comes from. So we end up with a row vector consisting of inner products. Well, remember, we're dealing with a symmetric matrix. So these inner products are going to involve orthonormal eigenvectors. So you're going to get a bunch of zeros. The only time you ain't going to get 0 out of these inner products is when I equals the index of the second one. So when, or maybe I say when the index on the second one equals I. So this will be 0, 0, 0, I. Entry will give out a 1, 0, 0, 0. That'll give you E sub I, where by this, I mean the ith standard basis vector. Written as a row vector here just because of the way the manipulations came up. So we're getting E sub i's out of this as row vectors. So if we take V sub I transpose V, perform that operation. That's going to give us E sub I, a vector of all zeros, except in the ith entry where there's a 1 followed by more zeros. Okay, when you take that row vector, multiply it by column vector B. Column vector B was introduced somewhere up here. There it is. Here's where column V came into the story. Default vectors are column vectors, unless I explicitly say otherwise, as we did down here. So vector B is a column vector. This little product here is actually produced a row vector. Take the matrix product, which is really just taking this vector of a bunch of zeros and a 1 as a row vector, multiplying it by that column vector B. We'll pick out B sub I, the ith component of vector B. All right, my apologies a little bit on the notation here. By B sub I explicitly mean the ith component of vector B. So that's what I mean by B sub I in this. Also, we're technically getting a 1-by-1 matrix out, but we've agreed with Gentle to treat 1-by-1 matrices as if they're scalars. So this piece, isn't it? Yeah, this piece of that product upstairs just produces a B sub I. Guess what? The stuff preceding it also just produces a B sub I. There's some transposes floating around, but when all the dust settles, that produces a B sub I as well. So we've got a B sub I out of those 3 things. These 3 things produce a B sub I, and then there's a C sub I left over. So that quadratic form we had written as this product of 7 different things. The first 3 give a B sub I, the second 3 give a B sub I, so we get a B sub I squared, and you've still got that eigenvalue C sub I floating around at the end. All right, we're in a setting of a symmetric matrix, a real symmetric matrix, so the eigenvalues are real. We made a claim about that in 3.8.7, gave a number of properties, that was one of them. So it makes sense to consider the maximum of those eigenvalues. Now, we mention real because there's no such thing as a maximum complex number in a set of complex numbers. Complex numbers aren't ordered by a greater than, less than, like the real numbers are. So I can't talk about one complex number being greater than another complex number. I can compare their norms, but I can't compare the complex numbers directly. Yeah, the norms are real numbers. I can compare real numbers. There's an ordering on the real numbers. So since we get real eigenvalues, it makes sense to say there's a biggest of these. Take the maximum of the C sub i's. I ranges from 1 to n, so I don't need any of that supremum stuff. I can just pick the largest one because it's a finite collection. So we can say that X transpose AX, this quadratic form, which we had written in terms of this sum, I'm going to pick, or how about this? I'm going to replace all those C sub i's with the maximum C sub I. Okay, by doing that, I pick up a greater than or equal to here. I could bring that outside of the summation after making the replacement. Hey, sum from I equals 1 to n of B sub I squared. Remember the B sub i's were the components of vector B. So here you're summing the components squared up. Well, that's the norm of the B vector squared. And we get that maximum C sub I thing out. So this allows us to put an upper bound in a certain sense on a quadratic form. We had X equals V times B and had substituted in X transpose X. So we do that substitution. We transpose the product, use the fact that V transpose and V inverse are the same. That's because the columns of V were orthonormal. It's an orthonormal matrix. V inverse times V disappears, leaves us with a B transpose B. Okay, so we've shown X transpose X equals B transpose B. If we take any non-zero X vector and the fact that the norm of X equals a norm of VB equals a norm of B. Exercise 3.7.c. Really, here's the argument right here. I mean, these are really x transpose x, that's the inner product of x with itself. That's the norm squared of x, and that's the norm squared of b. But that's how the proof of this exercise actually goes. Then, if we take x transpose ax, if we take this quadratic form divided by x transpose x, that is the inner product of x with itself, we can say that that's less than or equal to the maximum of the c sub i's. Take this inequality, or this inequality up here, divide it by the norm of b squared, or if you like, the norm of x squared. That produces this or this, and the inequality comes from up here, and you're left with a maximum on the right-hand side. This is brought up because for a symmetric matrix, the function r sub a mapping Rn into R, so it's based on quadratic forms, defined as R sub a of x, x transpose ax, x transpose x. I can interpret both of those as inner products if you like. We have to, of course, have x be non-zero because we get a norm of x in the denominator, can't divide by 0. This is called a Rayleigh quotient of matrix A. This is mentioned, I don't know how deeply it's done in linear algebra books, when we never cover this in linear algebra. There's too much other stuff to do. But this little paragraph is based on some stuff from Fraley and Beauregard's linear algebra book. Claim is the Rayleigh quotient is used in a numerical technique that approximates the eigenvalues of maximum modulus and their corresponding eigenvectors. I'm no numerical guy. Having upper bounds on eigenvalues, I know, is an important thing when dealing with certain differential equations. Eigenvalues less than 1 are good. They give convergence. Eigenvalues greater than 1, there's concerns over divergence in terms of solutions to certain kinds of differential equations. But anyhow, I leave it to the numerical folks to make use of the Rayleigh quotient. A little trivia more than anything here. This is named for John William Strutt, the 3rd Baron Rayleigh. He was a physicist that studied sound and optics, and is probably most famous for explaining why the sky is blue. The sky is blue due to a process called Rayleigh scattering. He's a co-discoverer of the element argon. It's a noble gas, isn't it? And won the Nobel Prize in Physics in 1904. But Rayleigh quotients, apparently of some numerical interest, and only useful when dealing with symmetric real matrices because of all the orthogonality stuff with the eigenvectors that underlie us getting to this little equation down here. All right, let's take a break on the videos. We'll come back and hopefully in only one more video be able to finish up this section. There's still a handful of proofs to do, but let's call it quits for now. Have a nice day.